So, today we are going to start the linearization of internal virtual work. Okay. So, remember we have to linearize both the internal virtual work and the external virtual work. Okay. So, we first start with linearization of the internal virtual work. Okay. So, you have to remember that the equilibrium equations are formulated in the spatial configuration. Therefore, the final discretization of the equilibrium equation, which is obtained after linearization, has to be formulated only in the current configuration or the spatial configuration. Okay. But the problem is, in the spatial configuration, the volume element dV is not known, okay, it is unknown. So, therefore, it is much more convenient to perform the linearization in the reference configuration, that is the undeformed configuration, okay, because here the reference volume, which is dV 0, is constant during the linearization. Okay. So, when you have to take the linearization, it means you have to take some derivatives, okay, and if you are taking the linearization with respect to the reference configuration, therefore, the integral over the volume, okay. So, that is basically constant, dV 0 is constant. So, you can take those derivatives inside the integral sign, okay, and then we can obtain the spatial linearized internal virtual work expression from the push forward operation of the material linearized equilibrium equation. Okay. So, we first do the linearization of the equilibrium equations in the material or the reference configuration or the undeformed configuration, and then finally, we use the push forward operations of various kinematical and kinetical quantities to get the linearized equilibrium equation in the spatial or the current configuration. Okay. That is our idea. So, now we know that the internal virtual work expression in the current configuration is given by del W, okay, and int for internal, which is a function of deformation mapping psi and the virtual velocity del V, is equal to integral over the current configuration of the double contraction of the Cauchy stress tensor with the virtual rate of deformation tensor. Okay. So, that we already know, and we also know that this spatial virtual work expression can be transformed to the material configuration, and this we already did in our kinetics, and when we were discussing the objective stress measures, and there we saw that the internal virtual work expression written over the reference configuration, okay, reference. So, B 0 and dV 0 is nothing but the integral of the double contraction of the second Piola-Kirchhoff stress tensor with the virtual material rate of the Green-Lagrange strain tensor. Okay. So, if you linearize this, you see the left hand side of both are same. So, if you linearize either of these expressions, you are going to get the same quantity. Okay. So, now if you take the directional derivative of equation 11, which means you have to take the directional derivative of this particular integral. So, the directional derivative of the internal virtual work in the direction of a displacement u or a change u in psi is nothing but the directional derivative of the integral of the double contraction of the second Piola-Kirchhoff stress tensor with the virtual material rate of Green-Lagrange strain tensor in the direction u. Okay. So, now as we said in our second point, okay, that now we know that we have to take the directional derivative of this integral. Okay. Now, in the reference configuration, your volume dV0 is constant. Therefore, this directional derivative, which will involve a derivative, can be taken inside. Okay. So, that is what we do. Because our volume is constant, I can take this directional derivative inside the integral sign. Then linearize internal virtual work in the direction u is nothing but integral over the reference configuration of the directional derivative of second Euler-Kirchhoff stress tensor double contracted with the virtual material rate of Green-Lagrange strain tensor in the direction u. Okay. So, this now is my integrand, which is nothing but the directional derivative. Okay. So, the next thing is we recall the product rule of directional derivative. Okay. So, if you have a set of nonlinear equations, okay, and these equations can be written as a product of two set of nonlinear equations G1 and G2, where this dot denotes any kind of product. It can be simple dot product, it can be double contraction. Okay. So, G is a product of two functions G1 and G2. Okay. Then we know, and this we had already discussed in our mathematical basics, that the directional derivative of G at a point x0 in the direction u is nothing but the directional derivative of G1 evaluated at x0 in the direction u dotted with, or the product with, function G2 evaluated at x0 plus function G1 evaluated at x0 dotted with the directional derivative of G2 evaluated at x0 in the direction u. Okay. So, why we are discussing this? Because we have to take the directional derivative of the second Euler-Kirchhoff stress tensor with the virtual material rate of Green-Lagrange strain tensor. So, here if you see, this can be our G1 and this can be our G2, and this double contraction is nothing but the product. Okay. So, now we have to take the directional derivative. This is what we have to take. So, therefore, I can use now the product rule of directional derivative to further simplify my internal directional derivative of internal virtual work. Okay. So, using this equation number 16, I can write equation number 13 as the directional derivative of the internal virtual work in the direction u is nothing but the directional derivative of del E dot double contracted with S in the direction u. Now, remember, S double contracted with del E dot is same as del E dot double contracted with S, because the eventual outcome of a double contraction is a scalar. Okay. So, it does not matter, you will get a same scalar. So, you can interchange both of them. Okay. It is just like A dot B is same as B dot A. Okay. Therefore, I can interchange. So, that is what we have done here. Okay. I have written the directional derivative of the virtual material rate of Green-Lagrange strain tensor double contracted with the second Euler-Kirchhoff stress tensor in the direction u is nothing but the virtual material rate of Green-Lagrange strain tensor double contracted with the directional derivative of second Euler-Kirchhoff stress tensor in the direction u plus the second Euler-Kirchhoff stress tensor double contracted with the directional derivative of the variation of material rate of the Green-Lagrange strain tensor in the direction u. Okay. So, that is what we get after applying equation number 14. Okay. Now, from our discussion on hyperelasticity, okay, that we had in our module on hyperelasticity, we had derived that the directional derivative of the second Euler-Kirchhoff stress tensor in the direction u is nothing but the material elasticity tensor C double contracted with the directional derivative of the green Lagrange strain tensor in the direction u. Okay. So, we have to find out the directional derivative of the second Piola-Kirchhoff stress tensor in direction u, and this is nothing but given by equation 16. So, I can now substitute equation 16 here, and then I can obtain the directional derivative of the virtual internal work in the direction u as del E dot double contracted with the material elasticity tensor C double contracted with the directional derivative of the green Lagrange strain tensor in the direction u, okay, plus our second term which remains as it is. Okay. Now, let us see the different terms in the directional derivative of the internal virtual work. Okay. So, from our discussion on the linearization of the kinematical quantities, we know that the directional derivative of the green Lagrange strain tensor, which is a function of the deformation mapping psi in the direction of a displacement say u, is nothing but 1 by 2 F transpose del u transpose plus del u into F. Okay. And now, we know that the small strain tensor is given by del u transpose plus del u. Okay. So, if I substitute this here, I can write the directional derivative of the green Lagrange strain tensor in the direction u as F transpose epsilon F. Okay. Now, we also discuss the case where we had very small deformation, okay, in case of say elasticity, okay, in linear elasticity, when the deformations are very small. In that case, F was nearly equal to identity, and we had discussed that the directional derivative of the green Lagrange strain tensor in the direction u is nothing but small strain tensor epsilon. Okay. So, now remember equation 18. Okay. Now, we have to evaluate this term. Okay. So, if you see equation number 17, we have evaluated this term over here. Now, we have to evaluate this term over here. Okay. Now, our objective is to evaluate the directional derivative of the virtual material rate of green Lagrange strain tensor in the direction u. Let us see how to do that. Okay. So, first we notice that the green Lagrange strain tensor is 1 by 2 right Cauchy green tensor minus second order identity tensor I. Okay. Therefore, if you take the material time derivative of the green Lagrange strain tensor, which is E dot, is nothing but 1 by 2 the material time derivative of the right Cauchy green tensor F dot. Now, I know that C is nothing but F transpose F. So, if I take the material time derivative del C by del T, which is nothing but C dot, it will be d by dt of F transpose F, and this will be nothing but d by dt of F transpose into F plus F transpose d by dt of F. Okay, and this is nothing but F dot transpose F plus F transpose F dot. Okay. So, that is what we have substituted and we have got. Okay. Now, the virtual variation of the material rate of the green Lagrange strain tensor is given by del E dot equal to 1 by 2 the virtual variation of the material rate of the deformation gradient tensor and its transpose plus multiplied by f plus f transpose, the virtual variation of the material rate of the deformation gradient tensor f. Now, we had discussed in our previous lectures that f, all the quantities are independent of the virtual variations. Okay. When you apply virtual velocities, these kinematic quantities like f do not change. Therefore, there will be no change f here. Okay. Now, we also note that the material time derivative of the deformation gradient tensor is nothing but del v by del x. Okay. So, this we had like d by dt of del x by del capital X. So, I can write this as del by del x of dx by dt, and dx by dt is nothing but our velocity. Okay. So, the material time derivative or the deformation gradient tensor is del v by del x, which in short can be written as the gradient. Okay. So, del 0 v. So, this del 0 denotes derivative with respect to the material coordinates. Okay. So, therefore, the virtual variation of the material time derivative of the deformation gradient tensor is nothing but the material time derivative of the virtual velocities, which in short is written as del 0 del v. Okay. So, we have also derived that the directional derivative of the deformation gradient tensor in the direction u is nothing but. Okay. So, this is the directional derivative of the deformation gradient tensor in the direction u is nothing but the material time derivative of u. Okay. And then if we now substitute, okay, now if we take the material time derivative or we take the directional derivative of equation 20 in the direction u. Okay. So, our equation 20 if you see was this. So, I have to take the directional derivative of this quantity in the direction u, because that is what we want to find out. Okay. So, this directional derivative of virtual material rate of Green Lagrange strain tensor in the direction u will be nothing but 1 by 2 del f dot transpose, the directional derivative of the deformation gradient tensor f in the direction u, plus the directional derivative of f transpose in the direction u times the virtual material rate of the deformation gradient tensor f. Okay. So, now I can use equation number 21 and equation number 22. Okay. In equation number 23 to get our required expression for the directional derivative of the virtual variation of the material rate of Green Lagrange strain tensor in the direction u as 1 by 2 del 0. Okay. So, material time derivative of the virtual velocities transpose times the material time derivative of the displacement or the direction u plus the material time derivative of u transpose times the material time derivative of the virtual velocities v. Okay. Now, we note that this term, the material time derivative of the virtual velocities, is a constant, since the virtual velocities are not a function of configuration. That we discussed in our previous lectures, that the virtual velocities are independent of the configuration. Therefore, we now, if you use equation number 24 in equation number 17. So, For simplicity, I have reproduced equation 17 here. Okay. So, equation 24 is the expression for this. Now, if I substitute equation 24, okay, which is expression for this, I will get the directional derivative of the internal virtual work in the direction u as the first term plus the integral of the second Pala-Kirchhoff stress tensor double contracted with 1 by 2 this term in the bracket integrated over the reference configuration. Okay. Now, we can further simplify this second term. Okay. I can further simplify it, and how I can simplify? I notice first that the second Pala-Kirchhoff stress tensor is a symmetric tensor. Okay. And then the term with which it has been double contracted, that is this 1 by 2 and this term in the bracket is nothing but it is the symmetric part of the tensor, second order tensor del 0 u transpose del 0 del v. Okay. So, if I take del 0, so it is a second order tensor, let us say if I write it as A, then A will be 1 by 2 A plus A transpose, okay, plus 1 by 2 A minus A transpose. Okay. So, you have this symmetric term and you have this anti-symmetric term. Okay. So, this is your symmetric term. Now, if I take double contraction of A with S, so I get S double contraction with this plus, so S double contracted with the symmetric part plus S double contracted with the anti-symmetric part. Now, we know that but double contraction of a second order symmetric tensor with an anti-symmetric tensor is nothing but 0. Okay. This we remember. If S is a symmetric second order tensor and W is an anti-symmetric tensor second order tensor, then this value is equal to 0. So, then what happens? This is equal to 0 and then the double contraction of the second Pala-Kirchhoff stress tensor with the symmetric part of second order tensor A is nothing but the double contraction of the second Pala-Kirchhoff stress tensor with the tensor A. Okay. So, that is what we substitute. Okay. So, this goes away and then you have the double contraction. Okay. So, that is what we have it here. So, I can substitute this with S double contracted with A, where A is my this expression. Okay. So, I can substitute this long, I can replace this long expression with this expression given by equation number 26. Okay. So, if I do this, my directional derivative of the internal virtual work in the direction u becomes the integral over the reference volume of the virtual variation of the material time derivative of the Green-Lagrange strain tensor double contracted with the material elasticity tensor C double contracted with the directional derivative of the Green-Lagrange strain tensor in direction u plus the integral over the reference volume of the double contraction of the second Pala-Kirchhoff stress tensor with the second order tensor given by this expression. Okay. So, now once we have this, we know further that there is a relation between the directional derivative and the material time derivative. Okay. So, what is this? To recall, the directional derivative of a nonlinear function f in the direction v is same as the material time derivative of the function f. Okay. Mathematically, if I write the directional derivative of f in the direction of velocity v is nothing but the material time derivative of f. So, equation 28 now implies the directional derivative of the Green-Lagrange strain tensor in the direction of the virtual velocities. So, it is still the velocity, but it has become now the virtual velocity will be nothing but the material time derivative of the virtual Green-Lagrange strain tensor, which is d by dt of del E. Okay. So, with this in hand, okay, I can replace, okay, the del E dot in equation number 27 with our equation number 29. Okay. So, our internal virtual work in the direction u will be the directional derivative of the Green-Lagrange strain tensor. Remember, this was nothing but del E dot. Okay. So, it becomes the directional derivative of the Green-Lagrange strain tensor in the direction of the virtual velocity is del V, double contracted with the material elasticity tensor C, double contracted with the directional derivative of the Green-Lagrange strain tensor in the direction u, plus as usually our second term. Okay. So, this expression given by equation number 30 is also called the Lagrangian linearized internal virtual work expression. Okay. And in theory, equation 30 can be used for the development of tangent matrix required for the Newton-Raphson procedure. However, it will be a very difficult task to do. Okay. So, what we now need to do is, we need to push forward equation number 30 to the spatial configuration, okay, and then we will get the Eulerian linearized internal virtual work expression. Okay. So, to push forward, there if you notice we have to notice that there are a lot of kinematical quantities, okay, like you have Green-Lagrange strain tensor, and that is their directional derivative. So, you directly cannot take the push forward of the directional derivative, that you have to derive. You have the kinetic quantity, the second Paylock-Kirchhoff stress tensor, and you have the material elasticity tensor C, that also we have to push forward, and also we have the kinematic quantity dV 0. Okay. This also we need to push forward. So, first we have to derive the expression for the push forward of each of them. Okay. So, once we do this push forward operation and we get the Eulerian linearized internal virtual work expression, we can derive the tangent matrix in much more simpler fashion. Okay. We will get a very elegant expression for tangent matrix. Okay. So, to carry out the push forward operation on the material terms in equation 30, we have to recall the following expression. Okay. We just saw that the directional derivative of the Green-Lagrange strain tensor in the direction u is nothing but the pullback of the small strain tensor epsilon, and how this pullback is given, it is F transpose epsilon F, okay, where epsilon is 1 by 2 the spatial derivative of u plus the transpose of the spatial derivative of u, that is the displacement. Okay. Now, we also know that the rate of deformation tensor D is the push forward of the material time derivative of the Green-Lagrange strain tensor, and the way this push forward is carried out is, you have to pre-multiply the material time derivative of the Green-Lagrange strain tensor with F inverse transpose and post multiply by F inverse. Okay. Therefore, I can get the push forward or the pullback of the material time derivative of the Green-Lagrange strain tensor as F transpose dF. Okay. So, what we are trying to do? We are trying to get the expression for various material kinetic quantities in terms of their spatial counterparts. That is what we are trying to get. Okay. Now, if we take the variation of the material time derivative of the Green-Lagrange strain tensor, we get F transpose delta dF, where delta d is the virtual variation of the rate of deformation tensor. Okay. Now, we also know that the variation of del E dot, that is variation of the material time derivative of the Green-Lagrange strain tensor, is nothing but the directional derivative of the Green-Lagrange strain tensor in the direction of the virtual velocities del V. So, okay, if we do this, we will get the directional derivative. Okay. So, if we compare these two, we get the directional derivative of the Green-Lagrange strain tensor in the direction of virtual velocities as F transpose the virtual rate of deformation tensor times F. Okay. So, in indicial notation, this will be helpful later. In indicial notation, equation 32a can be written as the term in the bracket ij, because the directional derivative of Green-Lagrange strain tensor is a material quantity. So, we use uppercase, then Fii del Dij Fjj. Remember, d is a spatial quantity, therefore, we have to use a small case indices, okay, lower case indices. Now, we know that the rate of deformation tensor is nothing but it is the symmetric part of the velocity gradient tensor L, okay, that is L plus L transpose by 2, or it is 1 by 2 del V plus del V transpose. Therefore, the virtual of the rate of deformation tensor given here is nothing but 1 by 2 the gradient of the virtual velocities plus the gradient of the virtual velocity transpose. Okay. Now, from our discussion in the kinetics, we know that the Kirchhoff stress is equal to the Jacobian times the Cauchy stress tensor sigma. Okay. And the Kirchhoff stress is nothing but the pullback or the push forward of the second Piola Kirchhoff stress tensor given by Fs F transpose. So, from this we already had derived that the second Piola Kirchhoff stress tensor is nothing but J F inverse sigma F inverse transpose. In indicial notation, I can write S I j, S is a material quantity. So, we use uppercase indices J F inverse I I sigma I j, sigma is a spatial quantity. So, we use lowercase indices F inverse J j. Okay. Finally, we have also derived in our discussion in hyperelasticity that J times the spatial elasticity tensor C is nothing but the push forward of the material elasticity tensor C. So, the spatial tensor C given by in indicial notation was given by Cij KL J inverse Fii Fjj Fkk Fll, then the material elasticity tensor C, okay, Cij KL. Therefore, I can write the material elasticity tensor C as J times Fii inverse, Fjj inverse, Fkk inverse, Fll inverse, Cij KL. Okay. And we from a discussion in kinematics, we know that the spatial volume dV is related to the material volume dV0 as shown in equation 37. Therefore, dV0 will be J inverse dV. Okay. So, now remember in our material equation, so our directional derivative of the internal virtual work in the material configuration, wherever we have dV0 Cij KL, the second Paola-Kirchhoff stress tensor, and the other kinematic quantities, we now can directly substitute these expressions, and if we simplify, we will get our spatial linearized internal virtual work expression. Okay. So, now let us do this. So, we are now ready to carry out the push forward of equation 30 to spatial configuration. So, for this we take our material linearized internal virtual work expression, which is given by this expression equation 30, we have reproduced again, and then we consider the linearization separately as term 1 and term 2. Okay. So, we separately push forward the both the terms, term 1 and term 2. Now, let us first take term 1. Okay. And we now substitute equations 31, 32b, 36 and 37 in term 1. Okay. So, our term 1 is shown here, and we now first what we do, we write this direct notation in equivalently into indicial notation. Okay. So, this is the directional derivative of the Green-Lagrange strain tensor in the direction of virtual velocities, and this is a second order material tensor. So, this is nothing but I j. Okay. So, the term in the bracket I j, and this is nothing but C I j k l, and this directional derivative of Green-Lagrange strain tensor in the direction of u is nothing but this quantity in the bracket k l. Okay. And now, I can substitute, for example, dV0 is J inverse dV, that is what we have done here. Then the directional derivative of E k l is nothing but F transpose epsilon F in initial notation is F OK epsilon OK epsilon OP FPL, and Cij is this expression over here, and the directional derivative of Green-Lagrange strain tensor in the direction of virtual velocities del v is nothing but Fii del d d I j F j j. Okay. Now, what I now do is I can further simplify, seems like a very big expression, but if we look closely we can simplify it further. Okay. So, I see that I have this deformation gradient tensor with an uppercase index I, and I also have another inverse of deformation gradient tensor with index uppercase index I. So, I can write these two as one bracket over here. Then I notice I have another deformation gradient tensor and this one. So, this again I can put inside the bracket. Then I have F inverse K M F OK. So, K is common. So, I can put these two inside one bracket, and now I have F inverse ln F P L. I have uppercase L common. So, I can write here C L K M is here, and our D I J is here. Our epsilon OP is here, and this J we can take on the right hand side. So, it becomes J J inverse dV. So, J J inverse becomes 1, and now I know that F inverse is identity, which means that F I F J I is nothing but delta I j. F inverse ij, okay. F inverse ij is delta ij, okay. So, now if I see this and I compare with this expression, I get that this expression is nothing but delta ik. The second expression therefore, also becomes delta Lj, the third one becomes delta Mo, the fourth one becomes delta Np, then delta Dij Ck Lmn epsilon Op dV. Okay. Now, if I now want to use the substitution property of the Kronecker delta, okay, I see that I have, okay, delta Ik and I have Ck. Okay. I have delta Lj and I have Clj. So, the first Kronecker delta will replace K here, the second Kronecker delta will replace L here, okay. And then I see that delta Mo epsilon O and I have delta Np and there is epsilon P. So, the third Kronecker delta will replace this O with M and the fourth Kronecker delta will replace this P with N. Okay. So, if I do this, I get delta Dij Cij Kl, okay, because K was replaced with I, J was L was replaced with J, M and N are already there, and O was replaced with M, and P was replaced with N. Okay. So, I get this expression, which in direct notation I can write the virtual rate of deformation tensor double contracted with the spatial elasticity tensor C double contracted with small strain tensor epsilon integrated over the current volume. So, now I have carried out the push forward of the first term. So, this was the term in the material configuration, and now equation 31 we get the term in the spatial configuration. Okay. So, the first term has now been totally pushed forward to the spatial configuration. Now, I take the second term which is over here. Okay. Now, let us take term 2. Now, first we notice that using the chain rule I can relate the gradient with respect to the material coordinates appearing in equation number 30 to the gradient with respect to the spatial coordinates appearing in equation number 30. Okay. So, now the material derivative of u is nothing but the spatial derivative times f. Okay. This is because del u by del x is nothing but del u by del x into del x by del x, and this is del 0 u, this is del u, and this is nothing but deformation gradient tensor. Okay. That is what we have in equation number 32. Okay. So, the material derivative of the virtual velocity similarly can be written as the spatial derivative of the virtual velocity times the deformation gradient tensor f. Okay. Now, if I use equations 32 and 33, I can write this expression. Remember, this is the expression with which the second Pawlak-Kirchhoff is being double contracted in term 2. Okay. So, this expression I can write del u f transpose into del v f. Okay. So, if I simplify, this become f transpose del u transpose del v into f. Okay. So, in indicial notation, equation number 34, which is this here, is nothing but, and remember this is nothing but the material tensor. So, therefore, we have capital Ij, and this f transpose if L f L I, and this is the spatial quantity. So, you have two small lowercase indices del u KL, and this is del V del V Km, and F is nothing but Fmj. Okay. So, equation 35 is the initial expression for the direct notation given by equation number 34. Okay. Now, the second term in equation number 30 using equations 34b, 35 and 37 can now be simplified, and that is how we do. Okay. So, this is the second term, okay, the double contraction of the second Piola-Kirchhoff stress tensor with the second order material tensor given by this expression. Okay. So, what I do? I first express this term in indicial notation. Okay. So, this is S I j del 0 u transpose del 0 del v I j. Okay. And now, I have already written this expression in indicial notation, and S I j we already know from 34b that how it can be represented in terms of the Cauchy stress tensor. So, I can replace S I j in terms of the Cauchy stress tensor. Okay. So, I can replace this with the Cauchy stress tensor, and this one now becomes this. Okay. And dV0 is nothing but J inverse dV. Okay. Now, as we did for the term 2, I can take first of all this Jacobian J on the left hand side, and then I have J inverse, therefore, this becomes 1. Okay. And then I have F inverse II, and I have F Li. Okay. So, this I can bring in inside one bracket. I have F inverse Jj, okay, and I have Fmj. These two I can bring inside one bracket. Okay. And then sigma ij multiplied by del u KL del V Km, del V Km. And from a previous discussion, we know that this is nothing but Kronecker delta del IL, and this second term is nothing but the Kronecker delta delta Jm, and we have sigma ij del u KL del V Km dV. Okay. Now, I can replace my L with I, because this Kronecker delta will replace this L with I, and this Kronecker delta will replace this M with J. Okay. Or I can replace I and J with Lm, it does not matter, because all the indices here are dummy indices. So, I have sigma Lm, or I could have written sigma Ij, this term in the bracket Ij. Okay. It does not make a difference. So, I have sigma Lm and this term in the bracket Lm dV. So, this is nothing but the double contraction in direct notation, the double contraction of the Cauchy stress tensor with the second order spatial tensor del u transpose del V. Okay. Now, we have the push forward of term 1 and term 2. Okay. I can write using equation 31 and 36. So, this is term 1 and this is the push forward of the term 1 to the spatial configuration. This was our term 2 and this is the push forward of the term 2 in the spatial configuration, and using this I can get the Eulerian linearized internal virtual work or the spatial linearized internal virtual work, okay, as this. Okay. So, remember this was the Lagrangian linearized internal virtual work, and now we get this expression which is nothing but the Eulerian linearized internal virtual work. Okay. So, this equation number 37 can now be used for the development of spatial tangent matrix, which is required for the Newton-Raphson procedure. Okay. And this expression, as I stated earlier, is also called the Eulerian linearized internal virtual work. Okay. Now, there are some more points to focus on, and one of them is we notice that the spatial elasticity tensor and the Cauchy stress tensor are symmetric, which means that the terms with the displacement u and the virtual velocities del v can be interchanged in equation 37 without changing the results. Okay. And consequently, the spatially linearized virtual work equation is symmetric in the displacement u and virtual velocities del v, which means that the linearized virtual work expression, okay, which is in the direction, I mean, of function of del v in the direction u is nothing but the directional derivative of the internal virtual work as a function of u in the direction del v. What this means is that eventually we are going to get a symmetric tangent matrix when we are going for the discretization. Okay. So, finally, we see the linearization of the external virtual work expression. Okay. So, the external virtual work expression is given by the external virtual work of the externally applied tractions and the virtual work of the externally applied body forces. Okay. Now, the external traction virtual work, which is this term over here, is nothing but the integral over the current area of the virtual work of the applied surface tractions T. Okay. So, T dot del V is the rate of which virtual work is being done, and then integral over the current area gives you the rate of external traction virtual work. Okay. So, the external body virtual work is nothing but the volume integral of the virtual work of the externally applied body forces B. Okay. Now, we have to linearize these two terms separately. Okay. However, in the present course, the external traction, which is T here, we assume that it is constant in magnitude and direction, which means that we are not considering any follower loads or pressure loads or any deformation depending loads. Okay. So, therefore, we do not have any follower loads. Okay. So, if we had a follower load, then it is a little complicated to do the directional derivative of such traction virtual work. Okay. So, in our course, we just treat that T is both constant in magnitude and direction. Okay. So, first we see the linearization of the external virtual work associated with the body forces, and one of the most common example of the body forces is the gravity load. Okay. There are other kind of body forces like the centrifugal forces, but here we take the simplest case of the gravity load. Now, in case the body force is given by the gravity load, then the body force vector P is nothing but the current density times the acceleration due to gravity g, okay, where g is the acceleration due to gravity and this is a constant. Okay. Therefore, we also know the relation between the density in the material configuration as J times the density in the spatial configuration rho. So, rho 0 is J rho. Okay. Now, writing using equations 39 and 40 in equation number 9, okay, which is the virtual external body forces, I can write my B. Okay. So, this is my B, I can write this as rho g, and from equation number 40 my rho is rho 0 by j g del v, and then dv can be written as j dv 0. Okay. So, this j and this j cancel out and I get the virtual work of the external body forces as rho 0 g dot with the virtual velocities integrated over the reference volume. Okay. Now, we notice that none of the terms is dependent on the current geometry in equation number 41. Okay. So, equation number 41, none of the terms. Okay. So, rho 0 is independent of the current geometry, g which is acceleration due to gravity is anyway a constant. The virtual velocities are independent of the geometry and dv 0 is also independent of the current geometry. Therefore, if we take the directional derivative, okay, so directional derivative of the external virtual work because of the body forces in the direction of displacement u, then what we get, because everything is constant on the right hand side, then the directional derivative is equal to 0. Okay. Now, linearization of external virtual work associated with the body forces. So, a number of different types of surface forces they exist, and the surface forces may both be constant in magnitude and direction, which means they are what is called dead loads, and linearization of the external virtual work of such forces is not needed. Okay. If you have dead loads, means everything is constant, then the directional derivative of the external virtual work because of dead loads will be equal to 0. And remember, we are not dealing with follower loads in this course, therefore, we will not have the directional derivative associated with the follower loads here. Okay. However, it is to be noticed that if the load depends on the current geometry, as in the pressure load where the magnitude is constant, but the direction changes, or in case the external loads are because of the contact forces, okay, which change both in the magnitude and in direction, then the linearization of the external virtual work will exist, okay, and it will then contribute to the tangent matrix which is needed for the Newton-Raphson method. In that case, equation number 43 will not be equal to 0. Okay. And the derivation for the directional derivative of the external forces of tractions because of follower loads or the pressure loads or contact forces is a very complicated exercise that we are skipping in this course. Okay. So, but you remember, if you have dead loads as your external tractions, then their directional derivative will be equal to 0, and if you have pressure loads or the follower loads, then your directional derivative will not be equal to 0, and you have to take that, and those forces, okay, follower loads will contribute to the tangent matrix they are also. Okay. So, they will have a contribution to the tangent matrix, and if you do not compute that correctly, then your convergence of the Newton-Raphson method will effect, okay, or will suffer. So, with this we end this module. Okay. Thank you.